Okay, good afternoon. Examples 16.1 and 16.2 of Christian are rather straightforward, so we won't try to spend too much time dwelling on those. Instead, let's try to first focus on example 16.5. Now, in example 16.5, we have here an example of a solution that is a mixture of two analytes. You have potassium dichromate and potassium permanganate. Now in this example, we're given two wavelengths. So let's try to write down our given in here. So what our problem says is that for potassium dichromate, it has an absorption maximum, let's refer to it as lambda 1, at 440 nanometers. And meanwhile, for potassium permanganate, it has its band at lambda 2. So that is equal to 545 nanometers. Now the mixture of the two is being analyzed by measuring the absorbance at these two wavelengths with the following results. So if we were actually able to use the spectrophotometer at this particular session, we can set its wavelength of light that it is emitting to our sample to 440 nanometers, have it shined into our solution, and let the spectrophotometer measure the absorbance. The absorbance here at 440 nanometers is A440, and its value is 0.405. And then resetting our spectrophotometer to a wavelength of 545 nanometers, we can measure the absorbance again of our mixture, and that value is A545 equal to 0.712. We take note that this particular set of values is for the mixture of the two. And all of this is being done in a 1 centimeter cell. So that gives us the value of our B, the path length, or the length at which the light travels as it moves through our sample, equal to 1 centimeter. Now we were given additional values in here as well. Additional values of absorbances listed here at the bottom. Let's also try to summarize those as well. So what the first two sets of values mean for us here is that for the chromium dichromate alone, when measured at 440 nanometers, without the presence of permanganate, its absorbance is just 0.374. And resetting our spectrometer to 545 nanometers, the dichromate by itself has an absorbance of 0.009. Now we can do the same. We can obtain another solution that only contains potassium permanganate, set our spectrometer to 440 nanometers, and measure the absorbance, and we find that that value is 0.019. Now for that same permanganate solution, we can remeasure its absorbance at 545 nanometers, and we find that its absorbance there is equal to 0.475. Now what's being asked of us in here is the concentrations in molarity, sorry about that, of the dichromate and the potassium permanganate. Now in this particular problem, we're given the absorbances of the pure solutions. So it might be na we have to start off our computation by using these values for the pure solutions. We recall from Beer's law. Beer's law is given as absorbance equal to the molar absorptivity times the path length times the concentration at any given wavelength. Now what we can try to do now is we try to check our given values to see what we have for this particular problem. Now for the pure dichromate solution, its concentration here is given to us. That's 1 times 10 to the negative 3 molar. So we can replace it by the following. So let me just erase that one. For potassium dichromate, we're given the following information. When it is just pure, we have a concentration of 1 times 10 to the negative 3 molars. Now, at a wavelength of 440 nanometers, we have an absorbance A, as said by here, equal to 0.374 for the pure dichromate solution. And the absorbance should be equal to the molar absorptivity of the dichromate at this wavelength times the path length, it's just 1 centimeter, times the concentration of our pure solution of potassium dichromate. That's 1.0 times 10 to the negative 3 molar. Now, let's try to compute the value of the molar absorptivity for this one. So we can simply divide both sides by this term over here, so that the molar absorptivity is given by 0.374 all over 1 times 1.0 times 10 to the negative 3. Now, if we plug this into our calculator, we should be able to get our answer for this one. So let me just input this one in my calculator. So from my calculator, I got a value of 374. Per the unit of B, that's centimeter, and divided by the unit of concentration, which is molar. So that is our molar absorptivity for the dichromate solution at 440 nanometers. Now we can do the same again for our second wavelength at 545 nanometers. The pure dichromate solution has an absorbance of 0.009. That should be equal to the molar absorptivity of the dichromate solution at this wavelength times the path length times the concentration so that the molar absorptivity at this wavelength is given by 0.009 divided by 1 times 1.0 times 10 to the negative 3. Now plugging that into my calculator, I get a value of 9 per cm per molar. Now you can also do the same for our pure potassium permanganate solution. So for the pure potassium permanganate solution, we can always try to compute again in the same manner the molar absorptivity of potassium permanganate at 440 nanometers and also the molar absorptivity of potassium permanganate at 545 nanometers using the same steps that we have done above for potassium dichromate. So if I plug this into my calculator, given the values that are written in my problem, so I should get the following values. So at 440 nanometers, the molar absorptivity of potassium permanganate must be 95 per centimeter per molar. By the way, it's a bit there. So you can see the concentration of potassium permanganate now. You can verify using your calculator if I've done this one correctly. And at 545 nanometers, the molar absorptivity of potassium permanganate can also be computed in the same way. So that should be equal now to 2,375 per centimeter per molar. So these values are very important to us. So we take note of them because these values are what we're gonna be using to compute the concentrations of the dichromate and the permanganate in the sample solution. Now, if you mix the potassium dichromate and the potassium permanganate together in one solution, you should be able to get something that looks a bit like this. Using the spectrophotometer, the computer that is connected to it should give you the following readout. The absorbance will be given to you on the y-axis, and on the x-axis are the various values of the wavelength that the spectrophotometer is able to generate. Now for my potassium dichromate, let's represent it as orange. So what I should be able to get would be something like this. If it was just potassium permanganate present in the solution, I should be able to get a readout that looks like this. It has its highest point or its peak at 440 nanometers. Sorry, that's not manganate. That should be dichromate over here, the one in orange. For my potassium permanganate, I should be able to generate a readout that looks like this if there was no potassium dichromate present. So its highest point is located at 545 nanometers. So this is the graph when our solutions are pure, i.e. when they are not mixed together. However, when you mix the two together, what happens here is that the absorbance of your potassium permanganate at 440 nanometers adds up to the absorbance of your potassium dichromate at that same wavelength to give you a reading that looks like this. So it's going to be higher than the pure solutions. And similarly, at a wavelength of 545 nanometers, the absorbance of the pure dichromate adds up to the absorbance of the pure potassium permanganate, so that your reading will now look something like this. The one that I just drew in purple. Now, absorbances are additive. That means to say that the total absorbance at any given wavelength, let's say at 440 nanometers, should just be equal to the contribution of the dichromate at that wavelength plus the absorbance of your permanganate at that same wavelength. Now in our solution, we do not know the concentrations of these yet, so we can't use the given values over here. Instead, what we now have to use is the value of the molar absorptivities we've measured earlier, just so we're able to find the items that we're looking for, which are the concentrations of our potassium permanganate and potassium dichromate. So when I plug this in, so for our mixture, I have the following. So at 440 nanometers, the absorbance of our solution is 0.405. That should be equal to the molar absorptivity of our chromium at 440 times B, that's still equal to 1, times the concentration of your potassium dichromate, plus, again using the Beer's law equation, the contribution of the permanganate is given by the molar absorptivity at 440 nanometers times B times the concentration of the permanganate. Now we've already computed this one. This is For the molar absorptivity of chromium, that's given as 374 times the concentration of the dichromate. Let's simplify this one. Let's just have it as X instead. Plus the molar absorptivity of our permanganate at 440 nanometers, we've computed earlier, that's equal to 95. Times the concentration of potassium permanganate, which we'll refer to here as Y. Now we can do the same for the total absorbance at 545 nanometers. So the total absorbance should just be equal to the contribution of chromium at 545 nanometers plus the contribution of permanganate at this same wavelength, so that I now have this particular expression. At 545 nanometers, the absorbance is 0.712. That's equal to the molar absorptivity of chromium at this wavelength times B times the concentration of the dichromate. Plus the molar absorptivity of permanganate at 545 nanometers times 1 times the concentration of the potassium permanganate. Now if we plug in the values that we've computed at the earlier stage in our solution, so we have, for the dichromate, its molar absorptivity is 9 times 1 times X plus, for our permanganate at 545, that's 2375 times Y, the concentration of potassium permanganate. We have two unknowns. We do not know the value of the X, and we do not know the value of the Y. However, we're given two equations in here. So these two equations, we can solve them simultaneously using systems of linear equations using our calculator. So solving equations 1 and 2 simultaneously, using our calculator, we should be able to get the following. So if you're using Casio FX991ES, so kindly go to Mode 5 and then press 1. So you should be able to see a table in our calculator, and I'll simply have to plug in the following. Under A, I'll write 374, press equal, I'll enter 95 next, press equal, and then I'll enter 0.405, equal. As to my second equation, I'll enter again the value under A, which is 9, equal button. 2375 equal button. And under C, I have 0.712 equal button. So inputting all of this, I should be able to get the value of x and y. For x, I have a value here of 1.008 times 10 to the negative 3. And for y, I'll press the equal button once more. I should get a value of 2.960 times 10 to the negative 3. Now, since in this particular problem, X represents the molar concentration of potassium dichromate, I therefore conclude that the molar concentration of our analytes are as follows. For potassium dichromate, which is equal to X, that is now equal to 1.008 times 10 to the negative 3 molar. And for my potassium permanganate, its concentration is given by Y, that's 2.96 times 10 to the negative 3 molar. And that's how we solve our example 16.5.